Somewhere in the Milky Way, a planet is drifting through space without a star. No sunrise, no sunset, no warm parent sun hanging in its sky. And yet, astronomers have now done something extraordinary. They've measured the mass of one of these wandering worlds. It weighs about 70 times as much as Earth, roughly 0.22 times the mass of Jupiter, and there's no evidence of a host star within more than 20 times the Earth-Sun distance. This isn't science fiction. The object is called KMT 2024 BLG 0792 OGLE-2024 BLG 0516, and its discovery was published in Science in January 2026. Researchers say it's the first free-floating planet whose mass has been precisely measured. But here's the strange part. They didn't photograph the planet. They couldn't see its surface. They didn't watch it crossing in front of a star. Instead, they caught something far more subtle. They caught gravity itself bending light. So how can a planet that gives off almost no visible light reveal its existence from thousands of light years away? And if this world is wandering alone, how did it get there? Because the answer may tell us something profound about how planets are born, and how easily planetary systems can fall apart. If that already sounds impossible, stay with this one. The most surprising part is how astronomers actually found it. For most of human history, planets seemed inseparable from stars. Mercury has the sun. Earth has the sun. Jupiter has the sun. Even the planets we've discovered around other stars appeared to follow the same basic rule. A planet forms within a planetary system and remains gravitationally tied to its parent star. But planetary systems aren't necessarily peaceful places. When young stars form, they're surrounded by disks of gas and dust. Within those disks, material gradually comes together, creating planets and smaller bodies. And once several massive worlds begin interacting gravitationally, things can become chaotic. Imagine a young planetary system filled with newly formed worlds, all tugging on one another. A massive planet can alter the orbit of a smaller one. A close encounter can fling a planet onto a radically different trajectory. And in some cases, that gravitational interaction can provide enough energy for a planet to escape its star entirely. The planet hasn't been destroyed. It hasn't disappeared. It's been kicked out. Astronomers call these objects free-floating planets, or sometimes rogue planets. NASA explains that gravitational microlensing provides one of the best ways to detect these otherwise extremely faint worlds. When one passes almost directly in front of a more distant star, its gravity bends and magnifies the star's light, creating a brief brightening. And that's the key. A rogue planet doesn't need to shine brightly. It only needs gravity. Before this new result, astronomers already had evidence for free-floating planetary mass objects. But there was a major problem. They were incredibly difficult to weigh, and that missing measurement mattered. Because without knowing their masses accurately, scientists couldn't confidently determine whether they were genuinely planets, distant objects orbiting stars, or something else. Then an unusual event appeared in telescope data, and the standard picture started to crack. The discovery began with something that, on its own, looked almost ordinary. A distant background star suddenly became brighter. Then the brightness changed again, and eventually it returned toward normal. That brief disturbance was a gravitational microlensing event. Here's what happened. The wandering object passed almost directly between Earth and a much more distant star. Its gravity warped the space around it. Because light follows the curvature of space-time, light from the background star was bent around the foreground object. From Earth, the background star appeared temporarily magnified. The planet itself remained essentially invisible. Think about the absurd scale of that. You're trying to detect an object that may be thousands of light years away, producing no obvious visible glow, by watching whether an unrelated star briefly changes brightness. And the signal doesn't last forever. For planetary microlensing events, the entire phenomenon can occur over hours or days. Once the alignment is gone, the signal disappears. The event was designated KMT 2024 BLG-0792 OGLE-2024 BLG-0516. But detecting a microlensing event wasn't enough. There was another problem. Astronomers normally face a mass distance degeneracy. The observed signal can make it difficult to determine both how massive the lens is and how far away it is. So how do you weigh something you can't see? The breakthrough came from observing the same event from different locations. Ground-based telescopes watched it from Earth, and the European Space Agency's Gaia spacecraft observed it from space. The two observing locations were separated by roughly 2 million kilometers, and the event didn't appear at exactly the same time from both vantage points. That tiny timing difference was incredibly valuable. It provided the geometric information needed to break the degeneracy. Suddenly, the invisible object could be weighed, and what the numbers revealed was extraordinary. The object came out at about 0.22 Jupiter masses, roughly 70 Earth masses. For comparison, Saturn is about 95 Earth masses. So this wandering world is considerably more massive than Earth, but somewhat less massive than Saturn. And here's where the discovery becomes more than just another strange planet. The researchers found no evidence for a host star within more than 20 astronomical units of the object. An astronomical unit is the average distance between Earth and the Sun. So we're talking about more than 20 times that enormous distance. That doesn't prove absolutely that the planet could never have a distant companion, but the evidence strongly supports the conclusion that this object is genuinely free-floating. And scientists had another question. Was this object actually born as a planet? Or could it have formed more like a brown dwarf, a much larger object that forms independently rather than inside a planetary disk? This distinction matters, because if this world formed in a planetary disk and was later thrown out, then planetary systems may be much more violent than they look today. So ask yourself, how many planets could have been born around stars, only to be kicked out before anyone ever had a chance to see them? And what would happen to a planet after billions of years wandering through interstellar darkness? Those questions become even more interesting when scientists looked at the object's properties alongside computer simulations. And that led to the first major clue about its origin. The researchers compared the event with the statistical properties of other microlensing detections and with models of planetary formation. Their conclusion? The object most likely formed inside a protoplanetary disk, the same kind of environment where ordinary planets form. Then something happened. Gravitational interactions likely pushed it out of its birthplace. Imagine a young planetary system before everything settles down. Several large planets may be competing for stable orbits. A smaller planet passes too close to a more massive neighbor. Gravity does not simply pull objects inward. It can exchange energy and angular momentum. One planet can move inward, another can move outward, and another can receive such a violent gravitational kick that it escapes the system altogether. This is a natural consequence of chaotic gravitational interactions. In our own solar system, scientists think the giant planets played an important role in shaping the orbits of smaller bodies during its early history. But we don't know whether our solar system ever permanently expelled an Earth-like planet. That's the important distinction. The new discovery doesn't tell us that Earth-like planets are routinely thrown into interstellar space. It tells us that planetary mass objects can exist without stars, and gives us direct evidence for at least one object that likely began life in a planetary system before becoming unbound. And once you picture the journey, the idea becomes haunting. A planet can spend millions or billions of years circling a star. Then one gravitational encounter changes everything. The star disappears behind it. The planet keeps moving. Its orbit becomes a trajectory through the galaxy. No star belongs to it anymore. No fixed sunrise marks the beginning of a day. Just darkness. But here's where it gets really interesting. Scientists aren't simply discovering individual lonely planets. They may be uncovering an enormous hidden population. This is the twist. The discovery of one precisely weighed free-floating planet isn't important only because of that one world. It's important because of what it suggests about all the others we haven't detected. Previous microlensing surveys had already produced evidence for planetary mass objects that might be free-floating. A NASA-backed analysis of 9 years of microlensing observations estimated that rogue planets could be extremely common in the Milky Way, with Earth mass and smaller worlds potentially making up a substantial population. The study estimated roughly 6 times as many rogue planets as stars in the galaxy, although that was a population estimate, not a direct count. That's an astonishing possibility. Our galaxy contains hundreds of billions of stars. If free-floating planets are abundant, there could be vast numbers of worlds moving through the darkness between them. But we have to be careful. We haven't photographed hundreds of billions of rogue planets. We don't know their exact number. And estimates remain dependent on the sensitivity and interpretation of microlensing surveys. What we do know is that gravitational microlensing has opened a window onto a population of worlds that traditional planet hunting techniques struggle to find. That's because most exoplanet searches rely on a star. The transit method watches for a planet crossing in front of its star. The radial velocity method watches the star wobble under the planet's gravitational pull. But a rogue planet has no nearby star to betray its presence. Microlensing changes the game. The planet can be almost completely dark, and gravity becomes the signal. And the newest discovery adds something scientists desperately needed: a precise mass. That means the invisible population is becoming measurable. But what exactly is happening during that tiny flash of light? That's where the real physics gets beautiful. Einstein's general theory of relativity predicts that mass curves spacetime. Light follows that curved geometry. So when the free-floating planet passes near the line of sight to a distant star, its gravity acts like a natural lens. The star doesn't physically become brighter. Its light is being redirected and magnified by the gravitational field of the foreground object. The observed brightness changes over time, producing a characteristic microlensing curve. From that curve, astronomers can extract information about the lens. But there's a catch. If you observe the event from only one location, different combinations of mass and distance can produce similar signals. That's why the Gaia observation was so important. Gaia and the ground-based observatories effectively looked at the same gravitational event from different positions. Because their locations differed by about 2 million kilometers, the geometry of the lensing event looked slightly different from each vantage point. That difference produced a measurable timing offset, about 2 hours, and that helped researchers determine the object's distance and mass much more precisely. This is an extraordinary way to discover a planet. We didn't see the planet. We saw what its gravity did to something else. It's like discovering an invisible person in a dark room because a tiny object suddenly moves when they walk past it. Except the room is the galaxy, and the object is a planet roughly 70 times Earth's mass. If this kind of detection fascinates you, hit like. It helps more people discover these strange stories from astronomy. And there's another reason this matters. This method can find worlds that other telescopes might never see. A planet doesn't need to reflect sunlight strongly. It doesn't need an atmosphere we can analyze. It doesn't even need to remain near a star. Gravity is enough, which raises an enormous question. Could these dark worlds actually be common? If rogue planets are abundant, then our picture of the Milky Way changes. For centuries, we imagined planets as members of planetary families. A star sits at the center. Planets orbit around it. Everything has a place. But free-floating planets break that picture. They turn the galaxy into something more like a vast ocean filled not only with stars and orbiting planets, but potentially with solitary worlds moving through the space between them. And that creates a fascinating question about planetary evolution. How many worlds are born normally but later expelled? How often does this happen? Does it mostly affect smaller planets? Could massive planets throw smaller planets out? And could some rogue planets retain moons? Scientists don't yet have complete answers. We also shouldn't confuse the discovery of a free-floating planet with evidence that it's habitable. This particular object is about 70 Earth masses. It's probably closer to Saturn in mass than Earth. We don't know that it has an atmosphere. We don't know whether it has moons. We don't know its surface conditions. And we certainly have no evidence that life exists there. In fact, a planet wandering far from a star would receive extremely little starlight. Any surface environment would be radically different from Earth's. But darkness doesn't necessarily mean absolute cold everywhere. A planet's internal heat can remain important, especially for larger worlds. And some theoretical studies have explored whether subsurface environments on rogue planets could potentially retain liquid water under the right conditions. That's an intriguing possibility, not evidence of life. And that distinction matters. because science becomes most exciting when we separate what we know from what we're still wondering about. And right now, the known part is already astonishing. A planet formed around a star may have been thrown out and spent its existence wandering alone. And we've finally weighed one. But we're nowhere near finished.